Hello, you're welcome. All right, so before us is static electricity. Okay. All right, now electricity is actually being divided into two categories. All right, we have the current electricity and that of the static electricity. Okay, so electricity is divided into two classes. All right, so we have the static electricity. That is where we are going to start. We're going to start with static electricity, and of course, we have the current electricity. Okay, so now the question is, what's the difference between static electricity and current electricity? Okay, now as the name implies, okay, static electricity is the electricity at rest. So why is it actually described as an electricity at rest? It is the type of electricity that is generated by a stationary charge, right? So such the charges in the static electricity, they are stationary, they are not mobile. All right. So in static electricity, what you have is stationary charges. All right. But in current electricity, what we have are actually mobile charges. Okay. Now, mobile charges are charges that can actually flow through a conductor. All right. So now we are starting with the static electricity. Then after which we're gonna talk about current electricity. Okay. So as I already said that I've already defined static electricity is the type of electricity that is generated by a stationary charge. All right. So now the question is, these stationary charges. Okay. Stationary charges. Okay, how are they produced? All right, so stationary charges are actually produced by friction. They are produced by friction. Okay, so what do I mean by that? Now, when you actually take a substance and rub it on another substance for a very long time, you are going to produce a stationary charge in those two substances, right? Yes, they are produced by friction when a material or a substance is being rubbed on another substance. Now, how is that possible? For example, let's say I got a sphere, okay? Then I have a rod of different materials, okay? Now, if I carry this rod and rub on this sphere for a very long time, okay, I'm going to notice that at the end of the day, this sphere will have a charge which is opposite to that of a rod. Okay, let's say the sphere actually acquires positive charge. If the sphere acquires positive charge, then the rod will definitely acquire negative charge. Now, what is the explanation of this? The explanation of this is actually traced to the the component of an atom. Okay, we know that an atom is made up of charged particles, which include the proton and the electron. All right. So now, anytime you actually take a material, let's say this material, let's say it's an ebonite rod. All right, ebonite rod, and let's say this is actually a silk material. All right, like a cloth. Now, each of these material they are made up of atoms, and these atoms actually have electrons. So when I actually carry this rod and rub it on the silk material, what happened? Okay, the silk material actually loses electron, and of course in chemistry, you are told that anytime an atom loses electron, it becomes positively charged. Okay, why? Because if an atom loses electron, that means it is having more proton than the electron, so that gives it a net positive charge. Now, the atom that actually accepts the electron, which of course in this case is the ebonite, okay, becomes negatively charged. All right. So the actual origin of electric charges actually comes from the transfer of electron. When a material is being rubbed on another, one material actually loses electron while the other accepts it. The one that loses the electron becomes positively charged, and the one that accepts the electron becomes negatively charged. Okay, so please take note of that. All right, so now this will actually lead us to what, okay, is known as the fundamental law of electrostatic. Fundamental law. All right, now the fundamental law of electrostatic or static electricity actually state that, okay, like charge, like charges, like charges actually repel. Okay, why unlike charges attract. So what does that simply mean? Of course, you know that we have uh, basically two types of electric charge, right? Types of electric charge. That is the positive and negative charge. You should know that. Okay. So electric charges is either right is positive charge or is negative. Right. So these are the two types. So from this fundamental law of electrostatic, we can simply say that if I bring a positive charge close to a positive charge, they are like charge. Okay. What you notice, the force between these two charges, okay, will be that of repulsion. So they will repel each other. But if I bring a positive charge close to a negative charge, okay, the force that you will actually that will exist between these two charges will be that of attraction. So that is the fundamental law of electrostatics. Okay, so which simply means that after this uh, transfer of electron from this sick to the ebonite, if you should bring the ebonite close to the sick, there's going to be an attraction, all right, and of course vice versa. Let's actually proceed. Okay, so now we are going to continue. So what we are going to be talking about another law, okay, of electrostatic, which of course is called Coulomb's law. Coulomb's law. Okay. Now, according to Coulomb's law of static electricity states that the force of attraction between two electric charges, okay, the force of attraction between two electric charges is directly proportional to the product of the electric charge. Let's say I have two electric charges, Q1 and Q2, okay, of quantity Q1, Q2. Q1 is the quantity of the first charge and the Q2 is the quantity of the second charge. So according to Coulomb's law, the force of attraction between those two charges, all right, let's say, let me just draw that. Let's say I have a charge Q1 of quantity Q1 and I have another charge Q2, okay, force that is separated by the distance r. Okay, so according to Coulomb's law, the force of attraction between Q1 and Q2 between two electric charges is directly proportional to the product of the charge and inversely proportional to the square of their distance apart. All right, the r is the distance between the two charge Q1 Q2. Okay, so of course in mathematics actually replace the proportional sign with an equal sign, then we have to introduce a constant of proportionality K. So that means force, electric force according to Coulomb's law is given as KQ1, Q2, okay, all over R square, okay? So I can still write that down, okay? Q1 is actually the quantity, okay, of the force charge, of the force charge. Then Q2 is the quantity of the second charge. Okay, where the R is the distance between the two charges. Okay, so the K is a constant I actually introduced due to the proportionality. Okay, so I can actually call that the electric force constant. Electric force constant. Okay, so now because it's a constant, it should have a constant value. Okay, now experimentally, it has been proven that the electric force constant, okay, um, according to Coulomb's, is equal to 9 times 10 raised to the power of 9 approximately. Okay, it's a constant. Then the SI unit is Newton meter square per Coulomb square. Now the question is, how did Coulomb's arrive at this constant? How did he actually, because it's a constant, there must be some parameters that actually give him the value of this constant. All right. Now the parameter that gave him the value of the constant is equal to the constant K is equal to 1 all over 4 pi. 4 pi, then E0 or epsilon 0. Okay. So it is the parameters after putting the value of these particular parameters, okay, and all of them they are constant, that actually give the constant K to be equal to 9 times 10 raised to power 9. Then of course you can try it. Of course you know very well that pi, okay, pi is a constant which of course is 22 all over 7, approximately 3.14. Then this particular symbol here, okay, I can use the symbol is epsilon, but you can use E0, okay. This symbol here represents uh, what is known as the permittivity of free space, permittivity of free space, or you call it the absolute permittivity. Okay, so now that simply means that, what does that imply? It implies that, okay, if we have permittivity of free space, okay, that simply means that this charge is located in it's actually in a free space. Okay, a free space is a space that is devoid of any material medium, like liquid, solid, and gas. Okay, uh, of course, A has almost the same value, okay, as the permittivity of free space. So A is almost regarded as free space. Let's say the charges is just found in air, right? Okay, so now that actually gives us the constant known as permittivity of free space, and by its value, it is equal to 8.85 times 10 raised to the power of minus 12. Then it has an opposite unit with this, Coulomb square per Newton, then per meter square. All right, so It is when this value pi, okay, then of course permittivity of free space epsilon zero is being put into this particular expression that you will now discover that, okay, the constant k is equal to 9 times 10 raised to the power of 9, okay. So invariably now it's either I write the formula of coulombs, the formula for electric force, okay, as this kq1 q2 all over r square, or I actually write it as this, okay. Electric force can also be expressed as this, since already we know that k is 1 over 4 pi epsilon 0, so it can also be given as k, k, okay, instead of k now, so I'll have q1 multiplied by q2, then divided by, already I have this as my k, that's 4 pi epsilon 0, then multiply by the r, okay, r square. So this is another way of expressing electric force. So I hope that is well understood. So what is really very important is to take note of this formula, and of course take note of this. All right, so we are going to look at some application. So I'll clean up. Let's look at example. Okay, let's look at typical example. So let's look at a situation where um, you have two charge of 2 microcoulombs, okay, and 3 microcoulombs separated by a distance of 20 cm, okay, and we are to evaluate the force between these two charge. So from the formula, force is kq1 q2 then all over r square, okay. So with what we have now, we put our values. K is constant, which we know is 9 times 10 raised to the power of 9. Then times Q1, the first charge, 2 microcoulombs. Now, remember, it is microcoulombs, the word micro, okay? If I have to convert microcoulombs to coulombs, I have to multiply by 10 raised to the power minus 6. So please take note of that. So if microcoulomb means that you have to multiply the 2 times 10 raised to the power minus 6. Then, of course, the same thing, 3 microcoulomb, that's 3 times 10 raised to the power of minus 6. All divided by the distance. The distance is 20 cm. Of course, you have to convert the cm to meter. And of course, to convert cm to meter, you divide the 20 by 100. So what you're going to have is 0.2. Okay? And of course, don't forget it's being squared. Square. Okay, so that's going to give me 9 times 2 times 3. 9 times 2 is 18. 18 times 3, I'm having 54. Then of course I deal with I just multiply the integers, all right. Then I can work with the powers of 10 separately using indices, all right. Of course, you know, by industrial law, okay, the powers of 10 have the same base and the base is 10, so all I just need to do is to add the powers, okay, since they are being multiplied. It's called addition law of indices. So that's going to be 10 raised to the power 9. I'm adding their powers now. 10 raised to the power 9 minus 6, then minus 6, then divided by 0.2 square will give me 0 point, excuse me, all right, that'll be 0.04. So let's finish up. So 54 divided by 0.04, I'm gonna get a calculator, okay. So I'm having now 54 divided by 0.04, that is 1350. So 1350, then of course times 9 minus 6 minus 6. 9 minus 6 is 3. 3 minus 6 is minus 3. So I'm having 10 raised to the power of minus 3. And of course, you know very well that 10 raised to the power minus 3 is reciprocal. It's the same as 1 all over 1000. 1 all over 1000. Okay? So if you divide 1350 by 100, you're going to end up having 1.350. Right? Then Newton. So you can use your calculator to actually confirm that. All right? So that is how we actually evaluate electric force. So I hope that is well understood. Okay. So please take note of the formula, and we're going to continue. We're going to look at the law of superposition of electric force in the next video. All right. See you in the next video. Thank you very much.